I will talk about quantum teleportation, the superdense coding, and the analog of this in operator algebra. This is a joint work with Samuel Harris and my advisor, Marius Junge. Samuel Harris is a graduate student at the University of Waterloo. So quantum teleportation and superdense coding are two fundamental protocols in quantum information theory that was introduced by Bennett and co-authors in early 90s. Basically, superdense coding says a procedure that one can use a qubit transmission plus a Bell state to realize two classical bit communication. And teleportation, on the other way, can use 2 bits classical transmission and 1 Bell state to simulate 1 qubit quantum communication. So here, I just want to provide a little bit explain this knowledge, terminology. That's a qubit here you can understand it as a density matrix in 2x2 matrices, and the bits is these diagonal matrices with respect to a fixed basis. And the Bell state, also called EPR pair or sometimes entangled bits, because this is the standard entanglement one can have, is given by this vector in 4-dimensional Hilbert space. And if you write down the density operator of this rank 1 projection, is given by these matrices. So this is just to make sure that you understand the expression precisely. And let's us review the protons of these two. So at the beginning, we assume Alice and Bob, they share a maximum entangled state of dimension 2, or it's just the E bits. And in superdense coding, Alice wants to send 2 bits of classical information to Bob. And the possibility come up is here the 0, 0 or 1, 0, 0, 1 or 1, 1. That's for 2 classical bits. And whatever she sees the classical information, she will apply accordingly a unitary to her part of the maximum entangled states. And that's basically here given by these Pauli matrices. And if she's in 0, 0, that means she does nothing. If she's in 1, 0, that's X, Pauli X matrices. If it's 0, 1, that's the Z matrices. If 1, 1, she does both. And whatever she does, she will send out her part of the maximum entangled state to Bob. Now, Bob will have both parts of this entangled state, but it's already modified by Alice. But is this modification, Bob can recover the classical information Alice wants to tell him by doing measurements corresponding to this column, which is orthonormal basis. Because it's orthonormal basis, Bob can measure perfectly to recover the classical information. So here, the superdense coding really means if with the help of these entangled bits, one can encode 2 classical information there into 1 qubit quantum channel. Without entanglements, one can at most do 1. So this is by Holevos bounds. The teleportation do the opposite thing, reverse the direction. Now Alice wants to send a qubit to Bob. And what she will do now is she will place the qubit she wants sent together with her part of maximum entangled states and do a measurements accordingly to, again, this maximum entangled basis. If you believe this calculation, then a measurements to the maximum entangled basis will now give this diagonal operator, and then this part of information is diagonal, can be sent throughout a classical channel of 2 bits. Then after Bob receives that, Bob will have this entire expression, and now he can correct his part of the state, the quantum state, accordingly to the classical singular he received from Alice. So here is again this trade-off by 2 classical bit transmission plus 1 entangled bit to realize the 1 qubit transmission is optimal. And without the entanglements, actually no quantum information can be encoded into a classical channel. And here the teleportation in this word means the phenomena that this singular state rho has not been sanded. It has been measured at Alice's sides and be reproduced at Bob's side. So that's the word teleportation means. So both these protons shows extraordinary power of entanglement in quantum information science, but it's also the entanglement alone is not sufficient to do any of these communication tasks. What it really implies is a coherent way to use different resources in quantum information, including classical communication, quantum communication, and entanglement together to do an information task. So this forms the cornerstone of the quantum resource theory developed by Devatak, Hayden, Winter, and many others. And also, the proton, the rays in the proton actually forms a fundamental trade-off limits of this resource. So far, that's all this operational meaning of these 2 protons. But as in the title, I'd like to talk about some operator algebra aspect of this story. So our starting point is really a joint work by Junge and Pasazoulis. They studied the complete boundary map of the maps in the protons. For that, I'd like to recall a minimal knowledge about the operator space that I need. So recall that the natural operator structure on the trace class and L1 sequence class is given by the operator space duality introduced by Efros-Rand and also Blanchard-Powelson. That's you can understand the dual space. You can understand the dual space of operator space by the complete boundary map to the scalar. And if you use this formula, it's actually not hard to see the matrix level norm of the L1 sequence is just the supreme of replacing the L1 standard basis vector by all the operators, all possible operators are contractions. And similarly, the matrix level of the trace class norm is given by the supreme of replacing the matrix units by entries of contractions. So here I also want to, so by that we understand the operator structure of, at least we have an expression for the operator structure of these 2 spaces. Then also just want to mention the complete boundary norm really means the supreme of the amplification of the original map tensor with a matrix space. So it does identity on the matrix space, and the complete boundary norm is the supreme over n, and if this is finite. So one particular consequence of Junge and Pasazoulis' result is a nice embedding theorem. That's the operators, as operator space, the Shelton class of d-dimensional matrices can be embedded into the MD of L1 d square. And this embedding, there is also another map, completely contractive map, send it back to the Shelton 1 class such that their composition are identity. So that means this space embeds as a completely 1 complement subspace. So this is a correspondence. If you see the map, that's basically the map comes from the quantum teleportation proton. And similarly, the second one is a correspondent to the superdense coding. That's the L1 d square can be embedded into MD S1D. And also, there's another complete contraction map such that their composition are identity. So this L1 d square is become a complete 1 complement subspace of MD S1D. And also, that's so all these maps, they're from the superdense coding and teleportation proton, except for the scaling constant here is different. Because in the proton, everything is quantum operation, so they are complete positive trace preserving map. Here, the constant difference is because if you look at this rank 1 projection of maximum entangled states, you put it into the space MD S1D, then in that case, it will has norm 1 of D instead of its trace is 1. So all these maps differ with the original Procton map by a scalar constant D. So to move into the C-star algebra category, our candidate is the smallest C-star algebra containing an operator space, or more precisely, a unital operator space. So that's this concept of C-star envelope. The C-star envelope of unital operator space is a C-star algebra together with a unital complete isometry, such that whenever you have another unital complete isometry to some other C-star algebra, you can always find a surjective star homomorphism and send it back to the C-star envelope, make this diagram commutes. And for this notion of C-star envelope, we actually know what's the correspondence for the L1 D square and the trace class. So recall that's the group C-star algebra of the free group of D generator is basically a universal C-star algebra generated by D unitaries. And then it has been observed that this L1 space, L1D space embedded in this C-star algebra completely isometrically in a natural way. You just send the basis vector to the generator. And then if you take a natural utilization by this one direct sum, then the C-star envelope of that is exactly the C-star algebra of the free group of D generators. And the other candidate is this Brown's non-commutative unitary algebra. Basically, it's the universal C-star algebra generated by the matrix entries of a unitary. And we also have a very natural like embedding of the shuttle. We have a very natural embedding of trace class space into the Brown's algebra. Basically, you just send the matrix units to the generator correspondingly. And here, if we take this subspace in spanned by the generator in the Brown's algebra, adding a unit to it, and you take the C-star envelope of that gives exactly back the Brown's algebra. But here, this unitization is different with the one before. So this lemma actually confirm our intuition that these two are the right candidates. So if you do a lifting map of the embedding, the operator space embedding, and you find out it actually becomes star homomorphisms of these algebras. So the B of D is corresponding to the trace class of D dimensional, and MD of C star algebra of FD, FD square. So now it's D square is corresponding to the MD of L1 D square. So here, since we have D square generator, we'd like to mark these as a double indices, like that way. And also for the seconds, we have the C-star algebra of the free group of D square generator has a star homomorphism into MD of the Brown's algebra. It's interesting that the proof is actually even easier than observe this star homomorphism. Basically, you just need to use the universality of these two universal C-star algebra. That you just need to check, okay, the image of the unitary generator are unitaries, and the image of the UJKs, they form entries of a unitary. So what do we have as our main result is actually more explicit expression that's related to these two C-star algebra. That we can have a matrix of C-star algebra of FD square is isomorphic to an iterated cross product of the Brown algebra by the Signe group ZD. And also, on the other way, we have the matrix level of the Brown algebra is isomorphic to the C-star algebra FD square. the iterative product of C-state algebra of SD squared, again by 2 copy of the ZD. So here the action, the first action alpha 1 is given by adding this phase factor. So because it has order D, so it's given action of the ZD. And the second action, which commutes with the first one, is by shifting both indices. And it also has order D. And the action beta is shifting the unitary generator, only shifting the first indices. And action beta 2 gives the shifting for the second indices index. And we also need to assume that the second action acts on the first copy of the ZD by the character action, like in the Takai duality. But our result is not in the region of Takai duality because the second action does not leave the algebra invariance. But we somehow observe this iterated cross product still realized a matrix structure, but in the other C-state algebra. With that, it's almost immediately to see the analog of superdense coding and teleportation in between these two C-state algebra. That's we can have the star homomorphism from the lemma are actually injective, and we have natural faithful condition expectation as there is a natural faithful condition expectation from the cross product to the algebra itself. If you do the composition of these two, you get identities. So this is, we think, is the analog of the superdense coding and teleportation in the category of the C-state algebra. So I like to give a sketch of the proof only for the first isomorphism. So the idea is to prove it by 2 steps. First, from the iterated cross product, we want to use a full cross product definition. That is, if we have the star homomorphisms and combine with the Pauli matrices X. So this gives a covariance representation of the first part of the cross product. And that will induce a star representation from the cross product to this algebra. And if you then use that together with the other Pauli matrices, it gives the covariance representation of the entire cross product. And if you have these two, then you have the isomorphism S1 tilde. Then after that, we want to apply the other star homomorphism from the lemma tensor with identity on the matrices. So for that, we want to show the composition of these two maps actually gives us a picture of the reduced cross product. So we check by simply calculate what's the image of the generators. And by this calculation, if you recognize this form, so recall this phi, negative L, negative N, they are all maximal entangled state. They form also normal basis. So it's not hard to see this picture is unitary equivalent to the reduced cross product. Now, since the ZD is an amenable group, so the reduced picture equals to a full cross product. So then these two composition has to be isomorphisms. So that's the sketch of the proof. We can also have the reduced version of the story. So McClanahan proved that the MD of the Brown algebra, D-dimensional Brown algebra, is isomorphic to the free product, the full free product of MD with the continuous function on the torus. And the map is given by sending the unitary entries to unitary entries, sending the fundamental unitary in the matrix of Brown algebra to the generating unitary of continuous function on the torus. And the third expression follows by the first two. Then the reduced Brown algebra is then defined by the reduced free product with respect to the unique trace on the matrices and the standard integral on the torus. So with this definition, we have the corollary that the action on the full system algebra can all be induced to the reduced system algebra. Moreover, we have our isomorphism result. So actually, this is just one more step than our full system algebra isomorphism results. If you can observe, if you recognize these algebras are actually GNS representation of the full algebras with respect to certain traits, like this one, the MD of BD reduced is basically the GNS construction, GNS representation of the full free product with respect to the free product trace. So if we can show, basically we just show the isomorphism for the full system algebra trace preserving. With this one more step, we can actually, then the rest of that follows by GNS construction. And for the von Neumann algebra, the Dagmar proved the following formula for the free group factors. And if we choose the k equals to 1 in his formula, then we have this expression. And if you combine that, if you compare that with the Mac-Knanahan's definition for the reduced Brown's algebra, then you actually find that the von Neumann algebra generated by the reduced Brown algebra is same with the free group factor, but with d-square generator. And our isomorphism results here merge to 1. So basically, we have the matrix level of this free group factor of d-square generator is isomorphic to doing a iterated cross product and also iterated cross product for the other actions. So this is the first part of my talk. Any questions so far? Okay. So then I'd like to move to my second topic with some applications of these isomorphism results related to quantum correlations. So quantum correlations are probability correlations arose from the measurements on quantum systems. Now we consider a bipart quantum systems. Then a correlation matrix is really, we have seen this from last talk, is really this is written in this conditional probability way. That is a connection of real numbers. It is called local if it can be written by convex combination of a product probability distribution. That's corresponding to the classical world. And in the quantum world, there are several competing definitions. The first one is the quantum spatial. If you can write the, so here the D, the indices D means the number of measurements at each party, and the M is the outcome of the measurements. So here we are using this projection value measurements, which is a family of orthogonal projection operator that sum up to 1. So each party has D copy of this, different copy of that. Then a correlation matrix is said to be quantum spatial if it can be given by a measurements, tensor product measurements on a vector in the bipartite state. And if it's a more general setting is quantum commuting, that's you can assume the states in one Hilbert space and assume the measurement from two different party commutes. Although the measurement all the E's may not commute, but every E commutes with the F's. And it says it's quantum if in either of the above case, the Hilbert space can be finite dimensional. So if we define the set of all correlation matrix arise from different settings like local, quantum, quantum spatial, and quantum commuting, we have so we have this hierarchy of correlation matrix that is a chain of inclusion. And we know, so basically the local correlation belongs to quantum belongs to quantum spatial, and the quantum spatial belongs to its closure, and its closure belongs to quantum commuting. Then we know all the sets are the convex, and the first and the last one are closed, and the closure is also naturally closed. The first observation that separates, provides a separation of one of these inclusion is the celebrity-Bayes inequality, and it's also served as an experimental test for entanglements. And the last inclusion is called the Trilson problem. Is asked whether the closure of quantum spatial equals to quantum commuting for every size D and M. So this is proved to be equivalent to the Kirchberger conjecture by Junge and Corsus and Freitas and Ozawa. More recently, Slofstra proves that for some large D, about 200, that these sets, this quantum spatial set, the correlation arose from the tensor product setting, is not closed, and this improved his previous results, that the correlation set of quantum spatial is not equals to quantum commuting. So this is the one I want to explore more, so the last one. So I want to mention a little bit more how this connection is made to C-star algebra. So if we denote that as the D-type free product of Signy group, and the quantum correlation matrix are exactly the restriction of the states of the tensor product of the group C-star algebra of that to itself. Restriction on the subsystem generated by the spectrum projection, just all the minimal projections in this C-star algebra. Then by that, we have a correspondence of the correlation set and to a particular kind of states on the tensor product C-star algebra. So the local will correspond to the separable state, but this separable is reading the meaning from physics, which is a convex combination of product states. And let's introduce two more notation. We say states of minimal tensor product of two C-star algebra is spatial if it can be implemented as a vector space while some spatial tensor product representation. If it's finite dimensional, if we leave this vector can be lived in some finite dimensional Hilbert space. So then the quantum correlation corresponding to finite restriction of finite dimensional states, and the quantum spatial corresponding to restriction of spatial correlation, spatial states, and this closure corresponding to the states of all minimal tensor product, and the quantum commuting are exactly the restriction of the maximal C-star tensor product. So this comparison between different states are really used in the original definition by Alvarez Lens to define the minimal and the maximal tensor product. So with this understanding, we can see the Slofstra's result implies there exists a non-spatial states on these algebras with the D to be large. And I like to consider the question, how about this phenomena for small D and M? So for that, I'd like to start with a parallel result by Cliff, Liu, and Powerson that they observe there's a non-spatial state on the minimal tensor product of the Brown algebra to itself. And it's given, it is characterized by these values. And basically, any states satisfy these values cannot be spatial in the minimal tensor product of Brown algebra to itself. And their results is based on a more interesting, maybe more basic phenomena that observed by Van Dan and Hayden in 2002. So what they observed is called this embezzlement of entangled states. Mathematically, I formulate it like this. So for n in n, there exists a finite dimensional Hilbert space Hn and a unit entangled vector in the tensor product space, tensor product Hilbert space, and the unitaries in the M2 by 2 matrices of the operators, such that if you apply this tensor product of two unitaries to this 0, 0 is like a non-entangled states together with these auxiliary states, then you end up very close to a maximum entangled states tensor with these auxiliary states that is closed by the Hilbert space norm. So what this embezzlement means is like we know these tensor product unitaries are local operations. They cannot create entanglements. So here the entanglements gain at this 0, 1 state parts is really the entanglement steal from the auxiliary states. But since we allow the amount of entanglements in the auxiliary state Rn growing, still a relatively small amount from these states will not change the states much with respect to the Hilbert space norm. So that's the idea behind this. So how this results is related. So basically, if you use this scenario and do a weak star limit points of these states, then you can approximate a vector. You can approximate a state on the minimal tensor product of B2 to itself. And moreover, Paulson they show that a perfect embezzlement, that this arrow is 0, cannot exist with this tensor product setting, even you allow this Hilbert space to be infinite dimensional. So for that, they can say, okay, any these exact values cannot be spatial. So our idea is to use our isomorphism results from the Brown algebra to the free group of C-star algebra to translate this non-spatial state to free groups. So we have the following diagram. That's here we have the non-spatial state here. Then the first row is the homomorphisms from the superdense teleportation and the superdense coding. We observe that these states fact through all the way here in a tensor product state form. And this row can be written as this row is a matrix in a 16-dimensional matrix, but it's actually only rank 2. It's actually only a Bell states. So the choice of this row is not unique, but here for simplicity, we choose a minimal rank 1. And with this diagram, then we can find these intermediate states. And we know this state cannot be spatial because if it's spatial, then psi will, this capital psi, if it's capital psi spatial, then psi will be spatial. So now we observe a states, non-spatial states on this minimal tensor product. But we'd like to translate it to, in this form, like a UCP map taking values in 2 by 2 matrices. So if we have this as the generator of the free group of F4, C-star algebra of the F4, then there exists a unital complete positive map such from the minimal tensor product of this C-star algebra to itself to the 2 by 2 matrices, and is taking value like this. And we know any psi satisfy this relation is not spatial. And here, the spatial for CPU map is basically means it admits a stance ring dilation via a spatial tensor product representation. So for that, I want, so basically from our diagram, we give a proof of that. But what was more interesting is a a very concrete scenario behind our arguments is we find out the following scenario. If we have a vector H0 belongs to a tensor product Hilbert space, and we assume that is controlled by two parties. Alice controls the Hilbert HA, and she has two choices to apply an operation, U0, U1. And Bob has control for the second Hilbert space. He also has two choices of operation. If they doing the operation accordingly, if they do U0 tensor V0 or U1 tensor V1, they will rotate these states to 45 degrees to one direction. And if we denote here the 90-degree vector is H1, which is orthogonal to the H0, so here is H0 plus H1 over square root of 2. On the other side, if they're doing the opposite operation, like U0 tensor V1 or U1 tensor V0, they are rotating exactly the opposite direction and also of 45 degrees. We observe this scenario exists if and only if both Hilbert space infinite dimensional. So that's the thing actually behind the previous theorem, the proof of previous theorem. Moreover, if we suppose there is another action that you can rotate 90 degrees by some other operations, we find out this entire scenario cannot exist, cannot happen with the tensor product setting, but it's possible with a commuting operator setting. So basically, the thing behind our separation is this two very concrete scenario. Based on that, we'll be able to show these results as a corollary that there exist non-spatial states on the C-state algebra of the free group tensor itself with more than 2 generators, and of the C-state algebra of D-tuple free product of the Signy group Zm, and minimal tensor itself, and for Dm greater than 2 and Dm not equals to 2. So the proof of that is we have an explicit violation of the spatialness by these values. And that's basically corresponding to this second scenario we show in last slides. And whenever you have these non-spatial states on F3, then you know the free groups with more than 2 generators contain each other as subgroups, and that extends to a non-spatial states on the other free group C-state algebra. And these states cannot be spatial because it's an extension of non-spatial states. And the same arguments applies for the free product of the Signy group. And this result is optimal because if you take the 2-2 case, that's this group isomorphic to infinite dihedron group, then this C-state algebra is a sub-algebra of M2 of the M2 of complex function on the torus, and on this algebra it's easy to see all the minimal tensor product states are spatial. How many time left?
5 minutes.
Okay. All right, so I'm about to sum up. So we show these two isomorphism results between the Brown algebra and the free group C-state algebra, and as an analog of superdense coding teleportation, we think this is an interesting appearance of entanglements in operator algebra category. And we also think this is related to some recent work by Harris that he proved the Brown algebra has an analog of Kirchberg conjecture, and the Brown algebra also has an analog of the Trelleson problem. And beyond that, we show the set of the spatial states is not weak-star closed for the tensor product of the free group C-state algebra, and also for the group C-state algebra of the free product of the Signy group if for small d and m. And we actually, this is not mentioned, but this is not mentioned in detail, but I just want to say we also obtain some separation of matrix value of correlation set for some small d and m. For example, we can realize so this matrix value, matrix version of quantum correlation sets is really the restriction of the UCP map onto the generating operator system. And what we can show, for example, is like you can show the 4x4 matrix values correlation sets on 4 copies of Z2 group or 4 two-outcome measurements. These correlation sets, the spatial one is not closed, is not equals to its closure. We also want to mention it remains open whether the Slough-Strauss separation, that the quantum spatial correlation not equals to its closure holds for all small d and m, as we see for the states. For the state we know, but this is really the restriction of the states witnessed on the generating projection subsystem. So that's what I want to say. For that, I'd like to thank you.
Some time ago, I classified all the teleportation and coding schemes for the matrix case.
Mm-hmm.
And that always amounts to, I mean, these objects are equivalent to, let's say, an orthonormal basis of maximally entangled states or a basis of unitaries.
Yes, yes.
Now, could you use any, so you seem to be using the Weil operators in that role.
Yeah.
Would these other solutions of the teleportation equations and so on, would they also give you the same isomorphism?
I don't know other form of teleportation. So
there are tons.
Oh, there are tons.
Very many possibilities.
Then I would like to know. Yeah.
Okay, I'll show you.
Yeah. Because that's the standard program. I only know that.
Sure,
yeah.
Sure.
Yeah.
But there are many others.
Okay. Yeah.
And they don't have to be based on a group, actually. So
okay.
You may have problems with your cross products.
Well, but that's very interesting. I think yes.
More question? Okay, so I'd like to thank the speaker again.